welcome to the deep dive. Think for a moment about how large language models, LLMs, have just completely changed everything about how we find information.
It's been pretty revolutionary, hasn't it?
Totally. It's like almost overnight, you suddenly gain this incredibly knowledgeable friend right there at your fingertips, ready to answer almost anything you could think of. But here's a really interesting thought. What if that friend wasn't just one brilliant mind, but actually an entire team of specialized experts?
Like a whole committee.
Exactly. Each one designed to handle a very specific part of your question, all working together perfectly, behind the scenes. That, right there, is precisely where the next generation of AI search is headed.
It's a fascinating direction.
So today we're embarking on a deep dive into this groundbreaking paper that really it lays out the blueprint for these cutting-edge AI search systems. And this isn't just about getting faster search results, not at all. It's about fundamentally changing how AI understands, how it plans, and then how it delivers the precise, reliable information you need.
Yeah, moving beyond just finding links to synthesizing answers.
Exactly. We're going to uncover some surprising facts and insights that I think are truly going to give you some major aha moments about where this is all going. Our mission for you, the learner, is to really distill the core mechanics of this next-gen AI search. We want you to grasp its multi-layered architecture, understand how it strategizes for even the really complex questions.
The tricky ones.
Yeah, the tricky ones. Discover its kind of ingenious methods for fighting misinformation, which is huge, and marvel at the incredibly clever ways it's becoming astonishingly efficient.
Efficiency is key at scale.
Absolutely. We're going to help you understand not just what these systems do, but how they pull off this complexity, and critically, why these advancements matter for your future information needs, how you'll interact with knowledge itself.
Okay, let's dive in.
Okay, let's unpack this. Imagine just for a second that your complex search query isn't just hitting one giant AI brain like one big LLM. Instead, it's hitting an entire team, a whole crew of highly specialized AI agents, all working together, like a perfectly choreographed orchestra or maybe a well-oiled machine.
Yeah, that's a good analogy.
This paper introduces what really feels like a complete paradigm shift in how AI search actually operates.
It really is. And what's truly fascinating here is precisely that move away from those single-agent LLM configurations we saw earlier.
Right, this sort of all-in-one model.
Exactly. In those older setups, a single LLM was often just burdened with too many complex jobs. Think of asking one person to be the researcher and the planner and the editor and the fact-checker all at once.
Yeah, that sounds exhausting. And probably error-prone.
It often led to task overload and, frankly, diminished efficiency, especially when you threw multifaceted problems at it, things that needed several steps. So by instead assigning these really well-defined, distinct roles to multiple LLM-based agents, this new system ensures a much clearer task allocation and really robust operational management.
Okay, so specialization.
Specialization, exactly. This modular approach, it actively prevents bottlenecks. Things don't get stuck waiting for one overloaded component. And it significantly enhances the overall performance and flexibility.
Flexibility. How so?
Well, you can swap modules in and out, upgrade specific agents, or tailor the team for different kinds of tasks without rebuilding the whole thing. It's a design that inherently reinforces scalability, too.
Right, so it can grow and adapt.
Precisely, allowing the system to maintain consistently high performance even with really complex, demanding queries, which, as you said, is crucial for real-world applications handling millions of requests.
Okay, so if we're sticking with this AI orchestra idea, who's the conductor? Who's the one taking my big, messy question and figuring out all the individual steps needed to actually get an answer, making sure everyone plays their part correctly?
That would be the planner agent. Its primary responsibility is pretty sophisticated. It takes your complex query, and this is key in a single efficient inference pass.
So one quick look.
Pretty much. It leverages a set of available tool APIs, kind of like a conductor scanning the available instruments, to generate what the paper calls a task graph.
A task graph. Okay, what does that look like?
It's not just a simple to-do list. Think of it more like a detailed, interconnected blueprint. It shows how to solve the query, mapping out dependencies between steps, what needs to happen first, what can happen in parallel.
Got it, like a project plan.
Exactly like a project plan.
Well,
Each vertex or node in this graph represents a tiny, actionable step, what they call an atomic schedulable subtask.
atomic meaning indivisible.
Yeah, the smallest logical unit of work. And these subtasks are interesting because they can do one of two things. They can either bind to an external tool, like calling a calculator API, or a dedicated web search engine.
Okay, like reaching outside the core AI.
Right. Or the subtask can be fulfilled by another agent, the executor, using its own internal LLM computation power for things like summarizing text or simple reasoning. Let me give you a concrete example. Imagine you ask something like, search the birth date of Emperor Hanwu, then search the birth date of Emperor Caesar, and finally, calculate the age difference between them.
Okay, a multi-step question.
Right. The planner wouldn't just try to answer that all at once. No way. Instead, it would dynamically break this down into, say, 3 distinct subtasks.
Let me guess. Search Han Wu, search Caesar, calculate difference.
You got it. Task 1. Search Hanwu's birth date, maybe using a web search tool. Task 2. Search Caesar's birth date, same tool perhaps. Task 3. Calculate the difference using maybe a calculator tool or internal computation.
And it knows the order matters.
Exactly. The graph structure defines that dependency. The calculation task depends on the results of the first 2 search tasks. This modular approach is absolutely key for handling questions that require multiple steps of reasoning or fetching external data points.
That's a really sophisticated breakdown. But okay, here's where it gets really interesting for me. How does the planner actually learn to be such a good project manager? How does it know if its plan is any good or if it, messed up the orchestration?
That is an excellent question, because optimizing an AI that's responsible for this kind of strategic decomposition, it's not trivial.
I bet.
The paper details this really sophisticated system of rewards that guides the planner's learning. They use a technique called Group Relative Policy Optimization, or GRPO.
GRPO, okay.
Think of it like a very meticulous coach giving really comprehensive feedback on every aspect of a team's performance, constantly refining their strategy based on outcomes.
So multiple types of feedback.
Yes, several layers. First, and maybe most obviously, you have final answer rewards. This is the ultimate goal, right? Did it get the right answer?
Makes sense.
So a positive reward is given if the entire multi-agent workflow produces the correct final answer when you compare it to a known ground truth answer. This ensures the system is fundamentally driven towards accuracy.
Accuracy above all. Got it.
Then there are user feedback rewards. This is where direct human interaction comes in, providing these invaluable signals.
So my feedback matters.
Absolutely. If you, as the user, accept the way it broke down the tasks, or if you like the final answer's flow, it gets a positive reward. If you reject it, maybe flag it as unhelpful, it gets a penalty.
So it learns what I prefer, not just what's technically correct.
Exactly. It learns to align with your preferences, adapting to what you find useful and intuitive over time.
Cool. What else?
We also have formatting rewards. This ensures the output isn't just factually right, but also presented well. Is it easy to read? Does it follow the requested format?
Usability. Important.
Crucial. Positive reward for correct formatting, penalty for bad formatting, because an accurate answer isn't much help if it's just a jumbled mess.
True.
And finally, intermediate execution rewards. This is about the plan itself. Each subtask in the planner's graph must actually be executable. Did this step succeed? Did the tool call work?
So it can't just create impossible plans.
Precisely. A score from 0 to 1 is assigned to the success of each subtask's execution. This actively encourages the planner to devise feasible, actionable plans, not just theoretical ones that look good on paper, but fail in practice.
Okay, so accuracy, user preference, formatting, and feasibility.
Right. And the overall reward is simply the sum of all these parts. This holistic reward function allows for really comprehensive optimization of the planner's complex decision-making. It's looking at the whole picture.
Wow, okay. So the planner maps it all out, creates this intricate blueprint, gets feedback, but who actually does the heavy lifting? The searching, the number crunching, calling those external tools. If the planner's the conductor, who are the musicians actually playing the notes?
That would be the executor module. It takes the planner's detailed instructions, that task graph we talked about, and it's responsible for actually invoking the appropriate external tool.
The calculator, the search engine.
Exactly. The paper shows icons for these: calculator, magnifying glass for search, weather app, map, pin. It calls these tools and executes the specific subtasks needed to produce the intermediate results that feed into the final answer.
You mentioned search is a big one.
Yeah, the web search functionality is highlighted as really critical and frequently used. It's essential for getting current authoritative information, Live gold prices, today's stock valuations, things that an LLM trained months ago just wouldn't know accurately.
Right, stuff that changes constantly.
Exactly. The executor handles fetching that fresh, real-world data.
Now, the paper talks about a paradigm shift in execution, referencing a figure 5. This sounds like a really fundamental change in how the system processes information. What's the big shift here compared to older systems?
Right. Figure 5 illustrates this really well. There's a fundamental shift in the executor's role, especially when you compare it to traditional pre-trained language model or PLM-based systems. The older way...
What did they do?
Well, PLM-based systems primarily handled a single query by basically turning it into a ranking problem. The goal was simple. Retrieve a bunch of documents, rank them, try to align the ranking with what they thought the user wanted, and show the top results.
Okay, standard search results page, more or less.
Pretty much. But this new AI search system, leveraging these more powerful LLMs, it often processes multiple queries or subtasks internally as part of the plan. And here's the crucial bit, the paradigm shift.
Yeah.
It reframes that traditional ranking problem as a recall problem.
Okay, recall problem. Unpack that.
So the objective shifts.
Yeah.
It's not just about aligning with user preferences anymore, like showing the single best link first. It's now about aligning with LLM preferences.
Meaning, what does the LLM need?
Exactly. The system's goal is to ensure the LLM, the core reasoning engine that's going to synthesize the final answer, has all the necessary pieces of information. It needs comprehensive recall of all relevant data, not just the top-ranked document.
So it's gathering all the ingredients for the LLM to cook with, rather than just showing me the top recipe.
That's a perfect analogy. It's about providing the LLM with a complete set of relevant facts it can then understand and synthesize into a coherent, comprehensive, and accurate final answer. It needs the whole context.
Fascinating. Okay, you mentioned these agents use tools and the executor does retrieval. But how do all these different pieces, maybe developed by different teams, maybe even different companies, how do they talk to each other smoothly? This sounds like a potential nightmare for interoperability.
You're putting your finger on a major historical bottleneck. Early tool-augmented LLM systems, they often relied heavily on vendor-specific function-calling JSON schemas. OpenAI introduced one, and then, well, many others kind of copied that pattern.
Right, I've seen those function calling APIs.
And while they were a step forward, they definitely led to significant fragmentation. Tools became tightly coupled to one specific provider's ecosystem.
Vendor lock-in, basically.
Pretty much. Plus, they often lacked strict, machine-typed guarantees, which makes reliable integration tricky. And crucially, it was really difficult, almost impossible, for independent agents, maybe from different organizations, to easily share tools or efficiently consider things like compute cost or security policies across boundaries.
Yeah, I can see how that would stall progress.
Absolutely. For complex AI search systems where the planner needs to orchestrate all these different lookups, computations, transformations in one big plan, this fragmentation was a major roadblock. It was like trying to build a complex machine with parts that all use different kinds of screws and connectors.
So what's the fix? What does this mean for us, the users, and maybe for AI developers too? Are we talking about like a common language for AI tools?
Yeah.
A universal API?
Exactly. That's precisely what the Model Context Protocol, or MCP, aims to provide. It directly addresses this fragmentation issue. It specifies a vendor-neutral interface based on standard web technologies, HTTP and JSON RPC. Through this standard interface, servers, think of them as providers of capabilities, can expose their tools and data.
Like offering a service.
Right. And clients, which could be LLMs themselves or the planner or other AI agents, can discover, invoke, and monitor these tools in a secure, structured, and standardized way. The paper mentions a server rack image, visually representing these servers hosting various capabilities ready to offer their functions.
So it standardizes the communication.
Yes, and MCP bundles 4 really crucial components to make this work smoothly.
Okay, what are they?
First, there's a manifest. This basically advertises what an endpoint does, its name, its purpose, semantic role, and even practical details like estimated cost and latency. This gives the planner critical info up front.
So it can choose tools wisely.
Exactly. Second, machine-readable input-output schemas. These are precise blueprints. They tell the client exactly how to call the tool, what data to send, what format to expect back. It grounds the LLM's function calling in solid data types.
It's reliable.
Third, a capability handshake. This is a mechanism for tools to sort of discover and negotiate interactions with each other if needed. Like they can introduce themselves and agree on terms.
Okay, and the fourth?
The fourth is an execution contract. This guarantees certain behaviors, like idempotency, meaning calling a tool multiple times, has the same effect as calling it once, which is important for reliability. And it ensures calls are auditable, providing accountability.
Accountability is good.
Definitely. And if we zoom out, this standardization through MCP is potentially foundational. Think about the impact HTTP had on the internet. It enabled massive interoperability, leading to the web we know today.
Yeah, a common standard unlocked everything.
MCP could very well be that for AI tools and services. It could unlock a whole new level of collaboration between diverse AI capabilities. Developers could mix and match tools from any provider, leading to an explosion of new, powerful AI applications for you, the user. It really paves the way for a more open, innovative, and versatile AI ecosystem.
That's a really powerful vision. Okay, let's circle back to the executor. Its role hinges on really good search and retrieval. How has that specific part evolved with LLMs? It sounds like the search itself is getting a major intelligence boost.
Precisely. Traditional LLM-based tool retrieval, or even document retrieval, often focused mainly on simple semantic matching. How similar is the meaning of the query to the description of a tool or the content of a document?
Okay, basic similarity.
Right. But for complex queries that require collaborative tool use, remember our gold stock currency example, or need information synthesized from multiple documents, that simple approach often falls short.
How so?
It might retrieve redundant tools, like we said, or it might miss crucial pieces entirely. It often fails to capture the completeness needed for these complex, multi-step tasks. It doesn't understand the relationships between the pieces needed.
Got it. So how does the new system do better? You mentioned LLM augmented features.
Yeah. In this newer LLM-based retrieval architecture, which the paper contrasts nicely with older PLM-based methods, they replace simpler language models with a more sophisticated, though still relatively compact, LLM. The source mentions using something like a Llama Tiny-based LLM.
Okay, still efficient, but smarter.
Exactly. This LLM generates much richer embeddings, those numerical meaning representations for both the queries and the documents or tools.
Richer how?
Well, here's the really innovative part. They use dedicated LLMs for queries and documents. The Query LLM incorporates user-specific features right alongside the query text. Think about your past searches, your preferences,
Personalization baked in.
right into the embedding. And the Document LLM integrates not just the document's content, but also document-specific attributes, maybe its source, its age, its type.
Metadata, yeah.
Exactly. This dual model approach captures way more context.
Yeah.
And a key advantage is how it seamlessly integrates features from multiple sources and even modality.
Modalities like images.
Yes. The Document LLM, for example, isn't limited to text. It can process images, maybe tables, other non-textual data, and create a single, comprehensive, unified embedding that represents that real-world content much more accurately.
Wow. So the embeddings understand text and images together.
Potentially, yes. This significantly enhances the accuracy and robustness of the whole retrieval system. It gets a much deeper understanding of both the query's intent and the content's meaning.
Okay, so the retrieval is much smarter. Now, once the executor gets this pile of potentially relevant documents, maybe hundreds or thousands, how does it quickly and fairly decide which ones are most relevant to pass on to the main LLM for generating the answer? It can't just be a simple ranked list anymore, can it? Especially for those complex questions needing multiple viewpoints.
You're absolutely right. A simple linear ranking often isn't good enough, especially for recall-oriented tasks or when fairness and avoiding positional bias are important. This is where the paper introduces a really fascinating concept called two-rank.
Two-rank, like a tournament.
Exactly. It draws direct inspiration from real-world sports tournaments, like the FIFA World Cup. Instead of just lining documents up and comparing each one to the query in isolation, it adopts a multi-round group stage format.
Okay, intriguing. How does that work with documents?
Imagine the retrieved documents are the participants. The system might seed the top documents, distributing them across different groups, just like in a tournament bracket. Then, within each group, multiple group matches happen in parallel.
And a match is?
A pairwise comparison. The LLM compares two documents head-to-head based on relevance to the query, or maybe some other criteria. Winner advances or gets points.
Ah, so the LLM acts as the referee for these document tools.
Pretty much. This parallel processing within groups allows for rapid identification of the strongest contenders, the most relevant documents.
Does it stop there? One round of groups.
No, and this is where it gets more robust. Documents can actually participate in multiple independent tournaments simultaneously or sequentially through rounds. Their final relevance score isn't based on winning just one match. It's aggregated across all the rounds and tournaments they participated in.
So it gets a more well-rounded assessment, less luck of the draw.
Exactly. It ensures a more fine-grained and robust ranking, less sensitive to one single comparison. It's like a team's world ranking being based on many games, not just one knockout match. And the key benefit, explicitly highlighted in the source, is the massive boost to efficiency and scalability. By allowing all this parallel processing comparisons happening simultaneously within groups and even across different tournaments, it drastically reduces the overall time needed to rank a large set of documents.
Faster results, more accurate ranking.
Precisely, ensuring a swift and accurate selection of the best documents for the main LLM to process. So yeah, forget simple lists, think high-stakes bracketology for information retrieval.
That's a fantastic analogy. I can almost hear the virtual commentators. And document 734 pulls off an upset against the highly seeded document 12. Okay, so these systems are becoming incredibly powerful, smart orchestrators, efficient retrievers. But what happens when the information they retrieve, even with tour rank, isn't perfect?
The messy reality.
Right. What if it's outdated or subtly biased or even deliberately misleading, fake news? In the real world, these noisy documents are everywhere. How do we make sure the AI remains trustworthy?
This is a critical question. How do we ensure the writer agent, the one that actually generates the final answer, you see, how does it stay robust and accurate when it's fed imperfect information?
Yeah, garbage in, garbage out is a big fear.
It is. So the paper proposes this really ingenious adversarial tuning approach. It's done within the multi-agent system itself, and they call it ATM.
ATM. Like the cash machine.
No, it stands for adversarial tuning in a multi-agent method. Think of it more like putting the AI through a really rigorous training camp specifically designed to build its resilience against bad data.
Okay, so how does that work? You mentioned adversarial. So there's an AI whose actual job is to mess up the documents. That sounds wild. Like hiring a sparring partner specifically to punch your main AI fighter.
That's a perfect way to put it, exactly. The ATM system has two core components: an attacker agent and a generator agent, which is essentially the writer.
Attacker and generator, okay.
The attacker's sole purpose is to deliberately introduce noise, perturbations, misleading info into the documents that the retriever finds. It tries to mimic the challenging, messy, sometimes deceptive nature of real-world information.
Trying to fool the generator.
Precisely.
Yeah.
And the generator, in turn, its goal is to withstand these adversarial attacks. It needs to learn to still accurately answer the questions, even when the attacker is actively trying to trip it up, demonstrating resilience.
Okay, how does the attacker attack? What are its tricks?
It employs two main strategies, becoming quite the master of deception. The first is fabrication generation.
Making stuff up.
Basically, yes. The attacker knows that the ARG generator, the part that uses retrieved documents to generate answers, can be sensitive to noise. So it mimics the style of high-quality documents, but it fabricates knowledge. This fabricated stuff might look relevant, be semantically related to the query, but it's actually useless or, worse, outright misleading.
Sneaky.
Very. It then strategically inserts these fake documents into the list the generator sees, making it harder to tell truth from fiction.
Okay, what's the second trick?
The second is list permutation. The RAG generator, interestingly, is also highly sensitive to the position of useful information within a list of documents. You know, the lost in the middle problem.
Right. If the good stuff is buried, it might miss it.
Exactly. The attacker exploits this. It randomly shuffles the document list. It might even duplicate some documents. This manipulation can push irrelevant or fabricated documents right to the top, effectively hiding or diminishing the visibility of the genuinely useful knowledge buried deeper in the list.
Wow, that's devious. So the generator has to deal with fake info and a messed up order.
Correct. Given a question and this list of potentially perturbed documents from the attacker, the generator takes them as input, its primary objective. Learn to identify and use all the truly useful documents while intelligently ignoring the noisy, fabricated, or badly positioned ones.
So it needs to build a really good filter.
A very good filter, yes. It needs to maintain its robustness and generate correct answers regardless of the attacker's efforts. Formally, the paper mentions an equation, equation 20, that basically says the generator aims to maximize correctness while minimizing the difference in its output, whether the input documents were clean or attacked. It learns to be consistent and right, even under pressure.
How is it trained to do that?
It's optimized using something called MITO-LOS, Multi-Agent Iterative Tuning Optimization. This involves a couple of key parts. There's a standard supervised fine-tuning SFT term, which helps ensure it still gets the right answer even with the TAC documents.
Okay, basic correctness training.
Right. But crucially, there's also a KL divergence term. This specifically aims to reduce the difference, the discrepancy, in the probabilities the generator assigns to answers when using a normal document list versus an attacked list.
So forcing it to be less sensitive to the attacks.
Exactly. It directly forces the generator to become robust, making it less susceptible to the attacker's tricks and more consistent in its output quality, regardless of the input's condition.
So it's not just about getting smart, it's about getting tough, like building up calluses mentally for the AI. This adversarial training sounds absolutely crucial if we want AI search we can actually trust, given how messy the internet is.
It really is. You can think of it like building an immune system for the AI, teaching it to recognize and filter out potentially harmful or misleading inputs, ensuring the information you receive is as reliable as it possibly can be.
Okay, so the system can find information, plan complex tasks, retrieve efficiently, and even handle noisy, misleading data thanks to that adversarial training. That's incredibly impressive. But what about the quality of the final answer, beyond just factual correctness? And critically, is it citing its sources properly? That's a huge sticking point for AI trust right now.
Absolutely. And that leads us directly into RVAG task alignment. This part focuses specifically on optimizing the output of the LM-based generator, or the writer agent. The goal here isn't just to spit out an answer, it's to produce a high-quality answer.
High quality meaning?
Meaning comprehensive, well-supported by the evidence it found, and crucially correctly cited.
Citations, yes.
So the paper specifies two primary optimization goals for what they call PA-AG, or Preference-Aligned AG.
PA-RAG.
Goal 1 is correctness, but in a specific sense here. The generator must fully utilize the valuable documents it was given. This means all the short answers or key facts contained within those retrieved golden documents, the best, most relevant sources, should actually be reflected in the generator's final output.
So no leaving important details out. Completeness.
Exactly. Completeness and accuracy based on the best available sources. Goal 2, equally vital, is citation quality.
This is the big one for me.
For many people, every significant claim or statement within the generated response must accurately cite the specific references that support that claim.
Like a proper academic paper, almost.
That's the direction. This is paramount for building trustworthy and auditable AI systems. We're moving beyond just getting facts to getting verifiable knowledge generation, allowing you, the user, to easily trace information back to its source. That's a massive leap for trust.
Totally agree. But how do they actually teach the LLM these very specific skills? Like knowing what key points to include from a source and how to format a citation properly. Its initial training probably didn't focus on that level of academic rigor.
You're right, it requires dedicated training. The process begins with an instruction fine-tuning phase. This is designed specifically to equip the generator with these fundamental ARG capabilities using retrieved info and citing it.
Okay, specialized lessons.
Yes, and it involves this meticulous three-step data construction process to create the training examples. First, they construct questions and find high-quality documents containing the answers, often sourcing questions and short answers from existing QA datasets.
Got it. Starting point.
Second, they identify the golden documents. For each question, the RA retriever first pulls, say, the top 100 most relevant documents from a huge database. Then, these are carefully filtered to keep only those documents that actually contain the known short answers or key facts for that question. That filtered set becomes the golden documents.
The verified good stuff.
Exactly. Third, they select prompt documents. From that golden set, they choose maybe up to 5 documents to actually use as input prompts during fine-tuning. They select these carefully to ensure they collectively cover all the required answers and are genuinely relevant to the query.
So it learns by seeing examples of good sources being used correctly.
Precisely. This iterative process builds that foundational understanding. Here's a question, here are good source documents, here's how you extract the answers, and point back to where you found them. Critical for trustworthy output.
Okay, that covers teaching the basics. But you mentioned user feedback earlier for the planner. How does human behavior, my behavior, directly make the writer better at its job? Especially in this complex multi-agent setup, we don't just want technically correct answers, we want answers we actually like and find helpful, right?
That's a crucial point for real-world usability. The AI search system actually frames this alignment with online human behaviors using the concepts of a Markov decision process, or MDP.
Okay, getting technical, but what does that mean practically?
Practically, it means your interaction, your behavior becomes the environment that the AI learns from. At each turn, the writer agent observes the state, which is basically your query in the context. It takes an action, generating a response, and then it receives a reward.
Based on what I do next.
Exactly. This reward comes from a specially trained reward model that interprets your subsequent actions. Did you click a link? Did you refine the query? Did you copy the answer? Did you just leave? This creates this powerful feedback loop. The writer continually adjusts its policy, its way of generating answers based on actual user acceptance or rejection patterns.
So it learns from millions of user interactions what works best.
Yes, but here's a really neat twist. Instead of just using numerical rewards, like +1 for good, -1 for bad, the system can introduce behavioral feedback directly as natural language instructions.
Like telling the AI in words what I liked or didn't like?
Potentially, or the reward model might generate that instruction based on your behavior. For instance, if users consistently ignore long introductory sentences, the feedback might translate to an instruction like, be more concise at the beginning. This is incredibly insightful because it leverages the LLM's core strength understanding and responding to text. It makes the feedback loop much more intuitive and powerful for direct human-AI collaboration.
That's very cool. Learning from language, not just clicks.
Right. Now, the core framework tying all this multi-agent learning together is called MMOA RAG. Big name, but
MMOA RAG. Let's break it down.
multi-module optimization with agent reinforced generation. The essence is the collaborative optimization of all the different modules, the planner, the executor, the writer, working together in the pipeline.
So they all learn together, not just individually.
Exactly. The objective is to align their individual optimization goals with the overarching task, producing a high-quality, user-accepted response. To achieve this, they often use a shared reward.
Shared reward.
Yeah, a common reward signal that all agents receive based on the final outcome. Often, this is something like the F1 score of the writer's final answer compared against the ground truth answer, F1 being a metric that balances precision and recall. So everyone gets rewarded if the final product is good.
Encourages teamwork.
Precisely.
Oh.
Now, to make this complex joint optimization work efficiently, there's a crucial first step. All the trainable modules, planner, executor, writer, first undergo that supervised fine-tuning, SFT, we discussed earlier, as a warm start.
Giving them a good starting point before the collaborative learning.
Exactly. This pre-training significantly improves how well they follow task-specific instructions right off the bat. It also drastically reduces the huge, complex exploration space they'd otherwise have to navigate during the multi-agent reinforcement learning phase. Makes the whole process more efficient.
So SFT primes them, then they learn together.
Right. The actual collaborative training, the reinforcement learning part, involves collecting rollouts, basically, running the whole system end-to-end on queries to see what happens. They collect sequences of states, actions, and rewards for each agent.
Okay, gathering experience.
Then they estimate the advantages, how much better an action was than expected, using techniques like GAE, Generalized Advantage Estimation. And based on that, they update the internal parameters of each agent's actor, its policy or decision-making function, and critic, its value function or assessment of how good a state is.
Standard RL components.
Pretty standard, yes. But the reward function for each individual agent is carefully constructed. It combines that shared reward based on the final answer, maybe some agent-specific penalties, like if the planner creates an invalid step, and a regularization term. This regularization term discourages the agent from straying too far from the policy it learned during that initial SFT warm start.
So that keeps them grounded while they learn to collaborate.
Exactly. It ensures that while the agents are learning sophisticated collaboration strategies, they also maintain and refine their core specialized competencies learned during SFT. It's a really sophisticated balancing act to make the entire system robust, adaptable, and effective as a team.
Wow. Okay, this entire system, multi-agent planning, execution, robust retrieval with TORANK, adversarial tuning against bad data, alignment with user feedback, collaborative optimization, it sounds incredibly powerful and incredibly complex.
It is complex, definitely.
Which brings me to a very practical question. For real-world applications handling massive scale, the paper mentions Perplexity processing over 10 million daily visits. This must require absolutely immense computing power. It sounds incredibly expensive to run. How on earth do these systems operate so efficiently without, bankrupting the company or making users wait forever for an answer?
That is the critical challenge for deployment, absolutely, of efficiency and cost.
Right.
And it's where these lightweighting methodologies become absolutely essential. How do you scale these enormous LLMs models with billions, maybe even trillions of parameters, like the Llama or DeepSeek models mentioned to handle huge user traffic while keeping latency super low and operational costs manageable?
Yeah, that's the million-dollar question, or maybe billion-dollar question.
Could be. The paper examines techniques specifically designed to optimize LLM inference. That's the process of actually generating an output from the trained model. These are crucial for making these systems practical. Broadly, these techniques fall into two main camps. First, you have algorithmic level optimizations. These focus on fundamentally changing the model itself, reducing its parameter count, its computational complexity, making the AI's brain inherently leaner and faster.
Okay, shrinking the model.
Right. Second, there are infrastructure-level optimizations. These focus on improving how the computations are performed, better workflows, smarter resource use, making the operational side, the AI's body, more agile and efficient.
Got it. Algorithm and infrastructure. Let's start with algorithms. We touched on attention earlier, the secret sauce, but computationally heavy. That seems like a prime target for optimization.
It absolutely is. Standard full attention, where every token looks at every other token, has this quadratic computational complexity, meaning if you double the input length, the computation roughly quadruples. Ouch.
Yeah, that scales terribly for long documents or conversations.
Exactly. It's a major bottleneck. However, a lot of research shows that, in practice, full attention isn't always strictly necessary. Often, only a subset of the context tokens really influences the output for a given token.
So you don't always need everything.
Often not. So, local attention mechanisms are a key approach. They restrict the scope of input tokens that each output token attends to, maybe just looking at a nearby window of words. This makes a computation significantly more efficient, often scaling linearly or near linearly instead of quadratically.
Okay, focusing attention locally. Are there specific examples?
Yes, the paper mentions a few. Light transfer identifies lazy layers in the model where attention patterns are already localized and selectively replaces the heavy full attention with more efficient streaming attention only in those layers. Reduces memory and computation while trying to keep long context ability.
Clever. Targeting the lazy parts.
Then there's Liger, which tries to linearize pre-trained transformers for faster inference. It repurposes existing weights to build recurrent gating mechanisms without adding new parameters, combining local attention with a linear recurrent part for both local detail and long-range dependencies.
Hybrid approach.
And low LCATS focuses on converting standard attention into something faster than quadratic, even for huge models. It uses a two-stage process to achieve this, leading to significant throughput increases, like up to 3x faster. So lots of innovation in making attention less of a computational hog.
Okay, smarter attention. What about the other algorithmic approach you mentioned? Making the model smaller. Pruning. That sounds like literally cutting parts out of the AI's brain, is that right? Making it smaller without losing its smarts.
That's essentially the idea, yes. Model pruning involves systematically identifying and removing parameters, connections, or even entire structural components from the model that are deemed unnecessary or redundant.
Without hurting performance too much.
That's the goal. Find the parts you can remove with minimal impact on accuracy.
How do they do that?
Several ways. The paper mentions layer collapse, LeCaux. This is a training-free method which is appealing that removes entire layers.
Wow, whole layers.
Yes. It cleverly merges the parameter differences between adjacent layers into a subsequent one, effectively collapsing the function of the removed layer into its neighbors. The cool thing is it can remove 30–50% of layers and act as a drop-in replacement. You don't need to change your code to use the pruned model.
That's neat. Training free is fast.
Definitely. Then there's CoFi, coarse-to-fine pruning. This approach simultaneously prunes at multiple levels, removing core structures like layers or attention heads and fine-grained units within them. It uses masks and distillation techniques to achieve high sparsity, like over 95% sparse, leading to huge potential speedups.
95% sparse, so only 5% of the original collections are left.
Potentially, yes, while aiming to retain performance. And another one, SlimGPT, adapts a classic pruning technique for LLMs, using a greedy algorithm to do structured pruning very quickly, maybe in just an hour on one GPU.
Yeah.
And it's task agnostic, making it versatile. So pruning is a major strategy for leaner models.
Okay, those are algorithmic changes.
Yeah.
What about the infrastructure side? You mentioned long outputs being an issue. I've seen that you ask a simple question and the LLM writes a novel.
Yeah.
How do they make responses more concise without losing the important bits?
Yeah, that output length is a major cost driver for inference. There's often this huge asymmetry, short query in, very long generated answer out. Reducing that output length is a primary tactic.
How? To tell it to be shorter?
Sometimes, yes. Explicit length constraint instructions like answer in N tokens or be concise can work to some extent, but there are more sophisticated methods.
Gotcha.
Techniques like length harmonizing rewards used during training. These rewards penalize outputs that are much longer than a reference answer, but they include accuracy constraints so the model doesn't just become short and wrong. There are also data sets specifically designed with length preferences, DLESTA, used for fine-tuning. Some models like Kimi even incorporate a length penalty directly into their policy optimization during reinforcement learning.
So actively training for conciseness.
Right. And related to this is compression of intermediate states. Sometimes LLMs generate internal thinking steps or chain of thought reasoning before the final answer. Techniques like Coconut, chain of continuous thought, or CODI focus on compressing this internal monologue or enabling the reasoning without generating explicit intermediate text, thus reducing the total number of tokens generated, which saves time and cost.
Making the thinking process itself more efficient. Clever. Now, what about repeated queries? I ask, tell me about the history of Hawaii. Someone else asks, what is the history of Hawaii? They're basically the same question. Does the AI have to rethink and regenerate that whole answer every single time? That seems incredibly wasteful.
You've hit on another huge efficiency lever, semantic caching. It's absolutely crucial for high traffic systems. As you said, AI search applications constantly see semantically identical or very similar queries. The paper mentions empirical studies showing around 31% of user queries exhibit this kind of similarity.
Wow, nearly a third are repeats, essentially.
Exactly. That's enormous potential for savings. Systems like Meancache, mentioned in the paper, tackle this head-on.
How does Meancache work?
It computes an embedding that meaning vector for an incoming query. Then it quickly compares this embedding to a cache of embeddings from previous queries it's already answered. If it finds a close match in meaning and the context is compatible, like it's not halfway through a different conversation, it just serves the previously generated cached response instantly.
Nice. And if it's a new query?
If no good match is found, it forwards the query to the main LLM, gets the answer, serves it to the user, and adds the query embedding and the response to the cache for next time.
Smart. Uses past work efficiently? What about privacy with caching user queries?
Good question. The paper notes they use federated learning to train the embedding model for the cache comparison. This allows the model to learn from user query patterns without the raw queries ever leaving the user's device or being centrally stored, thus preserving privacy while still enabling the cache.
Okay, that's important. Next, infrastructure technique. Quantization. This sounds like shrinking the model's data footprint, making it run faster and use less memory.
That's exactly it. Quantization is a very widely adopted technique. It basically reduces the numerical precision used to store the model's weights and sometimes its activations during computation.
Going from, say, 32-bit numbers down to
16-bit, 8-bit, which is very common, or even lower, like 4-bit or 3-bit in some research.
That hurt accuracy, using less precise numbers.
There can be a small accuracy trade-off, especially at very low bit widths, but techniques have gotten really good at minimizing this. The big win is the reduction in size and speed. Lower precision means the model takes up much less memory, RAM and VRAM, needs less memory bandwidth to read weights, and computations can be significantly faster on hardware that's optimized for lower precision arithmetic, like modern GPUs and TPUs.
So smaller, faster, cheaper to run. Makes sense.
It's a cornerstone of efficient LLM deployment.
Okay, one last infrastructure technique mentioned involves prefill and decode phases. You alluded to this. LLMs have different modes of thinking, and we can optimize each one separately.
Yeah, this is a quite sophisticated but really impactful. The LLM inference process, generating text token by token, can be pretty clearly divided into two distinct phases with different computational characteristics.
What are they?
First is the prefill phase. This is where the model processes your initial input prompt, your entire question, all at once. This part tends to be compute-bound, needing lots of parallel processing power to handle the prompt quickly.
Okay, digesting the input.
Right. Second is the decode phase. This is where the model generates the answer, token by token, auto-regressively. Each new token depends on the previous ones. This phase tends to be memory bandwidth bound, because for each token, the model needs to load its large weights from memory.
So compute-heavy start, memory-heavy generation.
Exactly. Recognizing these different bottlenecks, mature LLM inference frameworks, the paper mentions, Mooncake as an example, dynamically adjust the resources allocated to each phase.
How? Like having different servers for each.
Sort of. They might have separate pools of hardware, or dynamically reconfigure resources on the fly. They monitor the incoming request load and optimize the ratio of resources dedicated to prefill versus decode to maximize overall throughput and minimize latency.
So the system is constantly balancing its resources for optimal performance.
Precisely. It ensures optimal utilization of the expensive computational resources, avoids bottlenecks in either phase, and significantly improves overall throughput and responsiveness, which is absolutely critical for keeping those millions of daily users happy. It means the system adapts its internal workings to handle the load most efficiently. And the result of all these optimizations, this whole sophisticated system, the paper highlights really substantial improvements over older legacy search systems, particularly, as we noted, for those moderately complex and complex queries.
Where the multi-agent approach really shines.
Exactly. While it performs comparably for simple single-fact queries, this new AI search system achieves significant gains on harder tasks. The paper mentions a specific metric, maybe wins towards live or something similar, showing a 13% relative improvement for complex queries.
That's a solid gain.
It really validates the effectiveness of this whole architecture in satisfying those advanced user search needs, making it a true next-generation solution.
So wrapping this all up, what does this incredibly complex, multi-agent, optimized, adversarially trained system mean for you, the everyday person just trying to find information?
Yeah, what's the takeaway?
It means a future, and honestly, a present that's rapidly arriving, where your questions aren't just answered in a simple sense. They're deeply understood, broken down, researched by a specialized team, synthesized, fact-checked, and delivered by a highly coordinated, intelligent system. We're really talking about a significant leap.
From simple keyword search,
Or even basic chatbots, to comprehensive, reliable, and incredibly efficient AI-powered knowledge retrieval. Something that can tackle multifaceted questions with a level of accuracy and nuance we just haven't seen before at scale.
and if we connect this to the bigger picture, zooming out, these advancements, they move us far beyond just querying a big database or interacting with a single monolithic AI brain.
Yeah, it's more systemic.
Exactly. We're seeing the construction of truly robust, adaptive, and highly optimized systems that can tackle information-seeking tasks of unprecedented complexity. This relentless pursuit fact, multi-agent collaboration, building in adversarial robustness against bad info, radically optimizing for efficiency at every single stage, that's what will make AI search not just incredibly powerful, but also genuinely trustworthy and scalable enough for global adoption. It's fundamentally changing our relationship with digital information.
Which leads to a final thought, something for you, the listener, to maybe mull over. As these sophisticated multi-agent AI search systems become our primary way of accessing information, essentially serving as this always-on team of digital experts, how might our own strategies for finding information change?
Interesting question.
Will we learn to phrase our questions differently? Maybe ask bigger, more complex questions, knowing there's this complex orchestration ready to handle it?
Will we become better prompters of these agent teams?
Maybe. And how will the increasing ability of these systems, not just to find, but to reason, plan, and execute complex tasks, how will that reshape the very definition of what it even means to search for knowledge in this new digital age?
A lot to think about there. The definition of search is definitely evolving.
Indeed it is.